Hi everyone, I'll be presenting CHISEL, an optical slice of the wide area network. This work is done in collaboration with Bahl from NYSERnet, my advisor Rachee, and also some people from Microsoft. So the talk is structured this way. So first I'll give you some background and motivation, and then I'll talk about the challenges and show you some results. So 5G is ubiquitous. It offers high bandwidth, and all of us use it to stream content, browse social media, and also maybe upload some content. And your phone sends data to a cell tower over radio network, and the cell tower processes it using proprietary hardware. So using proprietary hardware has some issues like vendor locking, slow updates, and hard to maintain. This is because you need to do all of these things at the hardware granularity. So the 5G community moved away from this architecture to a newer architecture where your phone communicates with the cell tower on radio waves, but the cell tower processes the data on proprietary software instead of proprietary hardware, but on commodity hardware which is already available on the cloud. So this has advantages such as faster updates, easier maintenance, and the other advantages software gives you, but this comes at a cost because now you need to send your data from the cellular towers to the cloud data centers, and unsurprisingly this has very strict latency requirements. And we also know that 5G applications such as streaming, gaming, etc. have very strict network requirements for a reliable user experience. So network slices are a way to guarantee network requirements and have reliable end-to-end user experience. And today it's limited to the network between phones and the cell towers. But in the newer architecture, your 5G data path extends from your phone to the cell tower and to the cloud data centers over wide area network. And on the wide area network, we know that there are other kinds of traffic today, like broadband from houses, organizations, and there is no notion of slicing there, and as a result, there is no strong network guarantees, so it's hard to have end-to-end reliable user experience. In this work, we want to solve this problem because nobody likes buffering on their phone when they're watching Cliffhanger, right? So the first challenge to solve this problem is where do we slice the WAN? If we look at the network between the cell tower and the cloud data center, the bottom three layers look like this. So you have the optical layer at the bottommost physical layer, and then you have transponders which convert light to electrons, and then you have the network layer which implements IPv4 and IPv6. So you can implement slicing at two of these layers, at the bottommost layer using optics, or at the network layer using traffic engineering. So if we zoom in this picture, the green line is the fiber, and then the orange boxes are circuit switches which process light, and then the pink boxes convert light to electrons, and then you have packet switched routers which process electrons, right? So if you notice this diagram closely, a single port on the circuit switch is connected to multiple ports on the packet switch router. This is because a single port on the circuit switch can accommodate the entire light spectrum, which can accommodate up to terabits per second of bandwidth, but the latest packet switch router, a single port can accommodate a few hundred gigabits per second of bandwidth, so you need more ports on the routers to accommodate the same amount of traffic of a single port on the circuit switch. So now let's say we implement a slice using traffic engineering on this topology. It would look something like this. It will go through your circuit switch, gets converted to electrons, goes to the router, comes back, goes to the next circuit switch, again it gets converted, go to the router and come back again and leave the circuit switch. On the other hand, if we implement an optical slice, it will just go through both the circuit switches without incurring any conversions, and also not using ports on the packet switched routers, right? So as a result, using optical slices, you will use fewer ports, and then you'll also incur minimal conversions except at the source and the destination. This leads to direct cost savings. So to quantify this, we ran this experiment where on the x-axis I'm showing different number of slices, and on the y-axis I'm showing how many router ports were used if you were to use CHISEL and optical slicing or traffic engineering. We see that CHISEL constantly consumes less than 3x number of ports compared to traffic engineering, and then this is simply because CHISEL consumes ports only at the source and the destination and not in between. And this leads to cost savings because routers are expensive. So in this work, we argue that we should use optical slicing, and we build a system called CHISEL to do it. And then the reason is not just using fewer router ports. Turns out traffic engineering also has other issues. For example, to implement traffic engineering, you need to use priority queues on these routers, and there are very few priority queues today on these routers. And then queuing delay is inherent to packet switched networks. And as this leads to unpredictable and unreliable end-to-end performance of slices. So on the other hand, if we implement optical slices, you get predictable and stable end-to-end performance while using fewer resources. So to demonstrate this, we ran an experiment over 24 hours where we measured round-trip time between Ithaca and Syracuse on the same physical infrastructure on a wide area network. The blue line is the RTT of optical path, and red line is the RTT of the routed path. So we see that the RTT of optical path is not only lower, but it has lesser variation and way lesser jitter. And as a result, the optical path is more stable and gives you better predictable end-to-end performance. So in this rest of this work, we decided to use optical slices by programming optical circuit switches on the infrastructure, and now I'll talk about how we did it. So I've been talking about allocating bandwidth on the wide area network for 5G traffic, but we already know there's a lot of traffic on the wide area network already, right? So where will we get this extra bandwidth from? So to understand that, let's look at this graph. On the x-axis, we see the percentage of free spectrum on a fiber, and on the y-axis, it shows the fraction of fibers on Microsoft's topology that have so much free bandwidth, right? So we see that 75% of the links have more than 75% of free spectrum. So why is this the case? This is because the process of building this physical infrastructure is expensive. You need to identify where to lay these fibers, dig the land, hire people to do this, and all of this costs a lot of money, so compared to how much an individual fiber would cost. So when people do this, they typically tend to over-provision and then allocate spectrum incrementally. So for example, if I want to allocate this routed topology on this physical topology where yellow boxes are circuit switches and blue boxes are routers, for each of the edges in the routed topology, I would pick a different spectrum chunk, and then in the end, the spectrum on each fiber would look something like this, where the colored parts are occupied and the uncolored parts are free. So in this work, we want to use the free spectrum to accommodate 5G traffic and implement optical slicing. So now let's look at the next challenge. So how do we implement optical slicing, right? So there are multiple challenges in implementing slicing for 5G on the wide area network. The first challenge is a single 5G device is capable of generating 10 to 20 gigabits per second of load, and then as a result, just tens of devices joining or leaving the network can result in hundreds of gigabits per second variation in demands. As a result, we need very fast and on-demand optical slicing. And then there are also physical constraints of the optical spectrum itself on the fiber, such as we can only use free wavelengths and not the wavelengths used by other kinds of traffic on the wide area network. And then once we have the algorithm to, let's say, generate optical slices and the associated paths, we still need to implement it on the hardware, right? And the important thing here is we shouldn't disrupt existing traffic that's already on the wide area network, which is going through this hardware today. So let's look at a very simple example where we have two circuit switches and a fiber connecting between them, and then we just want to allocate one slice here. So light is a continuous spectrum, which is why it's divided into chunks typically. And the part of the spectrum which is used for communication today is around 4,800 gigahertz wide, and then it's divided into 128 chunks with 37.5 gigahertz per chunk. And each of these chunks are usually called wavelengths, and a single fiber can accommodate this entire spectrum. So the way you would allocate a slice is you would pick a free wavelength, and then you would pick a modulation format, and then allocate that modulation format for this wavelength, which decides how much bandwidth you get and how far you can reach without losing data. So now let's make this more complicated and realistic and such that it fits our problem. So we formulate our problem as a mixed integer linear program, which can be dynamically invoked when the demands changed. And then we borrow constraints from the physical properties of the network as constraints for this linear program. So the first constraint is we can allocate only free wavelengths on the spectrum to slices. And the next constraint is if there are multiple paths for a particular slice in the optical topology, we only pick one path because we don't want to waste resources. And then the next constraint is if multiple slices are sharing the same link, they need to use different wavelengths because there will be no way to distinguish the data between them otherwise. So in this example, the link between A and B is shared between two slices, AC and AB. They use different wavelengths 1 and 2. The next constraint is, let's say if a slice is using more than one link in the network, it needs to use the same wavelength on each of these links because we are routing our data based on wavelengths and it needs to be the same on all the links. So if a slice, then finally if a slice requires a lot of bandwidth, it needs to use the same set of wavelengths on every link that it's using. So I'll give you a brief overview of the algorithm with these constraints implemented. So the goal of the algorithm is to maximize the allocated bandwidth across all requested slices, and the inputs to the algorithm are a graph of the network topology where the nodes are optical circuit switches and edges are fibers, and then the initial spectrum state of every fiber, and then the slices and their associated paths, and what's the bandwidth request of each slice. So what the algorithm outputs is essentially this: which path is picked for a particular slice and what part of the spectrum on each fiber on that path is allocated to this slice. So if we notice it, the spectrum bitmap on the output is just one variable across all the links. This obviates the need to encode some of the constraints that I talked about and improves our algorithm. So once we have this, we can encode our goal as an objective. So we calculate the bandwidth of a slice by calculating how many wavelengths in the spectrum was allocated to this slice, and then we multiply it with the modulation format to get the bandwidth of the slice. And then once we have this, we maximize over all slice requests, all possible paths on that slice request, if the path was used and how much bandwidth was allocated to it. So now let's look at some results. So here on the x-axis, I'm showing different number of slice requests that were input to the algorithm, and on the y-axis it shows how many of those were successfully allocated. We see that for more than 150 to 200 slices, we successfully allocate more than 90% of the requests. And then the first graph was on Microsoft's network. We wanted to see how general our algorithm is, so we borrowed some open source topologies and ran the same experiment on that, and we show that on all these topologies we converge pretty quickly in less than 30 seconds for 200 slices. And then on Microsoft particular network, we show that for around 200 slices, we take less than 15 seconds to converge. So in the previous experiments, I was just picking slices with bandwidths between 50 to 200 gigabits per second. We wanted to see what will happen to the performance when we have larger slices. So in this experiment, we increased the granularity from 50 to 200 to 350 to 500, and unsurprisingly, it takes longer time to converge because you need to find larger contiguous chunks in the spectrum, right? So how can we reduce this? So it turns out there is something called as MIP gap in most of these solvers, which basically means mixed integer programming gap, the difference between the current value of the objective and the lower bound the solver has calculated for you. So by just setting a MIP gap of small values like 5%, you can converge in around 30 seconds. So the lower MIP gap you need, the more time you need to spend on the solver. So one of the issues with using the algorithm as is it leads to high fragmentation, and we know when there is high fragmentation, it's hard to allocate slices of larger granularity. So in this case, if you want to allocate a slice of 2 wavelength, it fails when there is high fragmentation, it succeeds when there is low fragmentation. So to handle this case, we added another part to the objective where we try to minimize the fragmentation, and we add a weight to that particular part of the objective. By tuning this weight, epsilon, you can decide what part of the objective you value more. So in this example, with different number of links in the network, we see what's the fragmentation index. Lower means lesser fragmentation with, as a result, by increasing the weight epsilon, we can reduce the fragmentation index. But if you look at the numbers next to those lines that indicate how many of the slice requests were allocated, that also reduces with increasing epsilon. So the lower the fragmentation you want, the lower also your slice allocations get. But there is a trade-off where you can pick small enough epsilon values so that your fragmentation is also small and more than 90% of your slices are allocated. So now once we had the output of these algorithms, we wanted to implement it on real hardware. So we wrote a script that can program hardware and implement slices, and when we tested it on 2 hardware setups, one is a setup in the lab, and another is the setup on a regional internet service provider production network in New York State called NYSERnet. So the main thing we wanted to evaluate was how does adding new wavelengths affect existing traffic on these networks. So on this first graph, on the x-axis we have time, on the y-axis we have quality factor, which means if the quality factor is higher than 7, it means the bit error rate of existing wavelengths is low enough that you won't lose any data. And this is the trace of production like traffic on the wide area network, and the quality factor remains the same even though we add and remove a new wavelengths between Ithaca and Syracuse during this time, right? And this particular graph, we were having only a few wavelengths, right? So we wanted to see what would happen if we exhaust the spectrum. So here we have 2 wavelengths on a lab test bed, and we measure its quality factor by filling the entire spectrum of the test bed. And we see that even though we go from 25% to 100% utilization of the spectrum, we see that the quality factor of existing channels remain the same. So to conclude, CHISEL demonstrated the advantages of optical slicing, and then CHISEL can quickly and dynamically allocate hundreds of optical slices. And then CHISEL's output can readily be implemented on commodity hardware today. And yes, CHISEL is also open source. Thank you.